All right, in the next video, or close to the next video, we're going to be doing the integration marathon. So like 120 integrals. But before getting into that video, I wanted to go over one more topic in relation to integration techniques. So the first integration technique we learned was the substitution method. And the way we learned it was that you look at an integral and then you identify a piece of the integrand, a piece of it, some expression of the variable, and then you see, okay, is the derivative of that piece, the resulting differential that comes out of it, is that differential, that derivative piece contained somewhere else in the integral? And if it is, then you make the substitution and it simplifies the integral. But the way that we talked about it, the way the textbook teaches it, in my opinion, it comes across as so once you examine an integral, if you don't see that, if you don't find a certain piece and whose differential is also in the integral, then you just say to yourself, okay, well, we can't do a substitution. The substitution method won't work here, so you go to the next integration technique. However, what you're going to see going through the integration marathon integrals is that in a lot of cases, you can use a substitution even though it doesn't line up in that ideal way of, you make the substitution and the differential is nice and clean in the integral and you go and it simplifies easily. Okay, so I wanted to give some examples of that here. And what I'm calling these are, so this is not the substitution method in that traditional sense of that, how it works out nicely. These are more of what I'm calling simplifying substitutions. Okay, and the way we're going to make the substitutions is very similar to what we learned whenever we talked about the rationalizing substitutions. We worked example problems on making these rationalizing substitutions, and what that was about was we were given the integrand was some sort of fraction, not a rational function, but a fraction with an x expression in the numerator, x expression in the denominator, and in most cases there was a radical with some x expression in it, and if you substituted, if you said that u was equal to the radical, the entire radical, and you simplified, you could turn the integrand into a rational function, which then you can solve. Okay, and so that's kind of the idea of that's the idea of a simplifying substitution specifically applied to turning something into a rational function. But we're going to use that same idea even if we don't have a fraction. We can use that same technique on any situation. So anytime we see a radical, whether or not it's in a fraction or not, you can think about substituting for that entire radical. Okay, just because you don't see the substitution doesn't work out cleanly to where the differential is in the integrand doesn't mean that you necessarily there's not a substitution that would be relevant to that problem. Okay, so for example, here, thinking about the traditional substitution rule, there's nothing we can do. There's no substitution we can make to where then the differential is, if we had an e to the x out here, then we could do something. We could say that u is equal to 1 minus e to the x, and then the differential of that is minus e to the x dx, and we have an e to the x dx, but we don't have that here. So again, after learning the substitution rule, we would just, if we didn't learn any different, we would just say, okay, we can't do a substitution. All right, but we see a radical, and it doesn't have to have a radical to do this, but that's a common situation where you see a radical and you substitute for the entire radical. But again, you don't have to have a radical, but that's a good place to start to try and get a sense for the simplifying substitutions. So we see a radical here, and we think, okay, what if we substituted, said u is equal to that entire radical? All right. Now, what we do here is we have a decision to make. Do we differentiate from this point, or do we can square both sides and do like an implicit differentiation? Well, we want to square both sides because We might want to differentiate from here. And when would we want to differentiate from this step? Well, if we had this square root of 1 minus e to the x in a denominator, then we would consider differentiating from this step, because we know that du dx is going to have, it's going to start with 1 over 2 times the square root of 1 minus e to the x. So we're going to have this in the denominator with the differential. But we don't have that here. So that would, differentiating at this step would make things complicated. So we're going to go ahead and square both sides. Okay, now we're going to do implicit differentiation. So take the derivative of this entire equation with respect to x. So we've got 2u du dx is equal to minus e to the x. Okay, and so now we want to solve for whatever we've got in the integrand outside of our substitution. So all we've got left is dx. So we want to just solve for dx. So we've got 2u du over, and so minus up here, and then e to the x is equal to dx. Okay, but this e to the x, we need to get rid of this e to the x. How do we do that? Well, we come here. Well, or here, we solve for e to the x. So what we can see is that e to the x is equal to 1 minus u squared. So we've got minus 2u du. And what we could do is we could switch this to u squared minus 1 and get, so 2u du okay, so now we can go ahead and make the substitution. So the square root of 1 minus e to the x is u. Okay, now and we're just left with dx. Okay, so take out the 2, and we've got u squared there we go. Now we can solve this. So you see how that we made a simplifying substitution, and it worked. But the way we started it, there was no, that just starting with the substitution and getting the differential right from here wouldn't have done anything. But substitution still worked. Let's take a look at another example. Okay, so here, with the traditional substitution method, we might say that u is equal to 1 plus root x. Okay, so du is equal to, but there's nothing we can do with this, right? There is no 1 over 2 root x dx. So we would say, well, the substitution method doesn't work, and we would go to something else. Okay, but we can actually solve this using substitution, what I'm calling a simplifying substitution. So let's still say that u is equal to 1 plus root x. Okay, so let's actually, we don't have a root x in the denominator, but still, we can still do this. So 2 root x. Okay, we can still do it this way. We just have to just do some algebraic manipulation. So what we've got is 2 root x du is equal to dx. Okay, but what is root x? Root x, we can see, is u minus 1. And we want to solve for dx because outside of the 1 plus root x, all we have left is dx. Okay, so now let's make the substitution. We've got u to the 8th times dx. And there we go. U to the 9th minus u to the 8th du, and we can integrate that. Okay, let's do another example. E to the cube root of x dx. Okay, so you can see these simplifying substitutions in a lot of cases involve radicals. You're substituting for either the radical itself or an expression containing the radical, but that's not always the case. There's cases that you could do simplifying substitutions that don't involve radicals. But, okay, let's say here that u is equal to the cube root of x. Okay, now let's cube both sides. Now let's take the derivative of the entire equation with respect to x. So 3u squared du dx is equal to 1. So 3u squared du, after the substitution, all we have left is dx. So let's solve for dx is equal to dx. So now what we've got is e to the u times 3u squared du. So 3u squared e to the u du. And we can solve this. Okay? So that's the idea of what I'm calling simplifying substitutions. Again, if we would have just taken the derivative, for the traditional substitution method, if we just take the derivative here, we're left with something that's not in the integrand. So the traditional substitution method doesn't work here. But a quote-unquote simplifying substitution does. Okay, the last thing I want to talk about is, so I've been mentioning when talking about integrating rational functions that, so the denominator in any rational function can, if you have the skills, the math skills, you can factor it into linear and quadratic factors no matter what the polynomial. However, with our basic knowledge of factoring that we learn in algebra, there's cases where we can't do that. We can't do this. Like if you run up with a factor of x to the 4th plus 1, using the knowledge that we have, we can't factor this any further. So yeah, in some cases we can figure out how to do it. So we saw if we had like x cubed plus 1 times x cubed plus 2, or maybe even x cubed minus 2, just to change it up. Okay, well, from the techniques that we learned in factoring at the beginning of the algebra playlist, we're not done here, because we have a sum of 2 cubes, x cubed plus 1 cubed, and so we would separate this out into a linear and quadratic factor. But this, we would say we're done, because we don't have a difference of 2 cubes, because the 2 is not the cube of anything. However, though, if we wanted to be smart, and we could separate this out, because we could write this as x cubed minus the cube root of 2 cubed. So we could use the difference of cubes formula with this being the cube root of 2. So we could be clever, and we actually could factor it. However, for something like this, we don't have a formula we can go by for like the sum of squares, right? X squared plus 1 squared. We don't have a formula for that. So we would need more skills to actually take this to actually factor this further. We would need, it's beyond the scope of what we learn in algebra and in this course, okay? And so what I want to talk about here is that if we have a polynomial where the denominator we can't factor it using the traditional means to linear and quadratic factors, then what do? Can we not solve it? Can we not integrate it? Sometimes we can't. However, what you do, though, if you get into that situation, then you look for a potential substitution. You still might be able to solve it with a substitution. Okay, so for example, so in this case, we have a rational function. The order of the numerator is less than the order of the denominator. And if we, so we would then want to factor this, right? So what we learned in factoring, how do we factor this? Well, we say that m is equal to x cubed. So then making that substitution, we've got m squared plus 3m plus 2. Okay, so then this is m 2, 1. All right, and so m is x cubed, so x cubed plus 2x cubed plus 1. Okay, now the sum of cubes, x cubed plus a cubed, is x plus a, x squared minus ax plus a squared. So we would say x cubed plus 2, and then x plus 1, x squared minus x plus 1. And this would be fully factored. But, you know, look, we couldn't get rid of it. We couldn't break this down into a quadratic or in linear factor. And again, we could if we use this same formula and wrote this as the cube root of 2 cubed. Okay, but let's just say we couldn't. Let's say we couldn't do this. Okay, well, that's an issue because now we can't do the partial fraction decomposition. Okay, so again, does that mean we can't solve it? Well, no. If you look, we could say that we could make a u substitution and say that u is equal to x cubed. Therefore, du is 3x squared dx. So 1/3 du is equal to x squared dx. We have an x squared dx here. So bring out the 1/3. We've got, so u squared is x to the 6th plus 3u plus 2. There we go. Now we can solve this. All right, let's take a look at another one. Okay, so we've got a 5th order polynomial in the denominator, 0th order in the numerator, but you can see we fully factor the denominator, and we can't get to strictly linear and quadratic factors. So we can't do partial fraction decomposition on this. So what do we do? All right, well, you do a simplifying substitution. You try and work with it. So if we said that u is equal to x squared, then du is 2x dx, and we want to, so we're going to go ahead and solve for just dx. So du over 2x is equal to dx. Okay, but we need this. We need to make this x a function of u. So what is x? Well, we can see that x is equal to the square root of u. So we've got du over 2 root u is equal to dx. Okay, so making the substitution, we've got x is equal to root u. X to the 4th, that's u squared. Okay, now we just have dx, that's okay. So we've got, bring out the 1/2. Root u times root u is u. And there we go. Now we can solve this, right? And so I hope this helped to illustrate how, and you're going to see this in the integration marathon. You're going to see a lot of examples of this, but you know, there's kind of 2 ways you could look at doing substitutions. The traditional way, where you know you say u or whatever is equal to some expression in the integrand, and then you go ahead and take the derivative right there, get the differential, and that differential is also in the integrand. That's the traditional substitution method that we learned. But then there's another way of looking at substitutions where it doesn't happen that way, but either by just playing with the differentials, and you define the variable to be some function of x, then you can solve for x and play with the differentials and kind of move things around, and you might end up transforming the integrand into another integral that you can solve.